thank you very much for this very warm introduction and for the welcome. I'd like to begin by thanking the department for having invited me to be here. As a matter of fact, we have a two-day official meeting on Friday and Saturday that is organized by Prof here. And so I just thought that I would use this occasion also to tell you a little bit about what I've been doing. As you know from the introduction, I'm not an alumnus of this department, but an alumnus of the Department of Chemical Engineering. But I have taken advanced physics courses from this department, so I consider myself an honorary alumnus of this department, and 2 out of the 3 courses were taught by Professor Balakrishnan, so it really is truly a humbling experience for me to be speaking here with one of my teachers in the audience. So if I don't do a good job of this talk, then you know who to blame, you know. So let me start this stopwatch here because I would not like to exceed my time. So I'm here to tell you a little bit about what motivates some of this research work and what it is that we have achieved in the past couple of years. So I work in the field of elementary particle physics, and the bread and butter for us is the evaluation of what we call Feynman integrals, and one of the 2 courses.
Do you have a phone somewhere near the microphone?
No, my phone is over here. Is there a problem?
Change the location.
There's a feedback, is it? Okay. Yeah, okay, you be my timekeeper, all right? So that's the stopwatch. Yeah.
That's not it.
Yeah. 2 mics. I don't need this mic. Let me just get rid of it. Eduthottuma. Idu venama. Okay. And just turn this off. Yeah, I can take my timer back. Yes. So, are you able to hear me at the back? Yeah. Okay. So the object of interest to us in elementary particle physics are these objects that are known as Feynman integrals. One of the 2 advanced courses I did was on quantum field theory, so I won't say it again. So in the process of learning to use techniques to evaluate Feynman integrals at higher loop order, and if possible in analytical form in the various variables that enter such a Feynman integrals, we had to explore many different techniques. And it turns out that the techniques that we've had to develop also enable us to evaluate other integrals of interest to physicists and mathematical physics in general, which explains part of this title. And they have an intimate relation to what are called hypergeometric functions. And we are all aware of the series 1 plus x squared, the basic hypergeometric, the geometric series that we are all accustomed to. There are generalizations of these which were first done by Gauss in the 19th century, which he termed as hypergeometric functions. And these are ubiquitous in the evaluation of many of these integrals in the variables. But it turned out that when we were doing this research, that we were not able to find many implementations on well-known platforms such as Mathematica. So during the course of this work, we also decided to develop Mathematica codes, which we have now published and made available to the community at large. So just a few words of introduction, because we have a diverse community over here. Just to say, what are Feynman diagrams? Well, Feynman diagrams are, of course, diagrams, things of this sort. They are made up of lines like this, which have what we call internal lines, and it also has external lines. And each of these internal lines is what we call a propagator in the subject. And depending on what kind of structure and topology this thing has, there are various names. This is called a 2-point function, for instance, because there are 2 external lines. This is called a tadpole. Sounds like a biology seminar, but that's the name that is given because it just jumps out and goes back to itself. It has no real external legs over here. This is a triangle, and this could show up in a physical process like one particle decaying into 2 particles like so. So this is called one loop because there is a loop over here. This is called a one loop 2-point function because there's a loop. And here is an example of a 2-point function which looks similar to this, but there are 2 loops drawn over here, and it has a rather attractive type name of a sunset diagram. So this is the kind of diagrams that we will be talking about. Now, whenever you encounter a diagram of this sort, there are very definite mathematical rules which tell you what to do with a diagram of this sort. For each loop, there will be an integration over a volume or a d-dimensional volume element, and for each internal line that you see, you have a denominator that goes as 1 by k squared minus m squared, where k is the momentum that is flowing in this loop and m is the mass of the particle. So a diagram of this kind, for instance, will have a momentum flowing in, and then it has two internal lines, and in principle you could have two different masses. For each one of these describes a virtual particle that jumps out of the vacuum. So there may be two mass scales in this particular diagram, which you may call m1 and m2. In this case, for instance, there's one external momentum, but this other two momenta are not independent because everything adds up to the momentum carried by this external line. And you may have three masses in this particular problem. In this case, you have a momentum that flows in, and you have again three different masses. So these are the various variables that we are accustomed to, that we have to deal with in problems of this kind. Now, a lot of this material is known to people here, especially because some of my students had Sunetra and Suresh as examiners of the thesis, so it's not a real surprise for any of them to see some of these things. So let me just proceed a little bit and just tell you that when you actually evaluate these diagrams with these specific rules that I just mentioned, they also satisfy, interestingly enough, they satisfy differential equations in the various variables associated with this particular diagram. For instance, here is this bubble diagram that we had over here. If k is the external momentum, then it satisfies pictorially such a differential equation. And then it turns out that this this one loop bubble diagram has certain factors like this, where d is the dimension. We don't evaluate it in 4 dimensions because these things happen to be divergent. So you don't want to deal with that divergence. So you just say that, let me just extend it to a number of dimensions called d, and then later I will let d go to 4, which is the physical case. Here is the mass of this particle. So a bubble gets related to a tadpole, and here we see this function that is familiar in math methods courses. For those of you who have not bought Professor Balakrishnan's book, I urge you to do this. You will run into functions like this. This is the Gauss hypergeometric function that I mentioned, which has parameters typically called a, b, and c, and I will explain this a little bit more. And x is the variable out here, where x here could be this k squared. And this tadpole itself is expressed in terms of gamma functions that we all know in our BSc and MSc courses. And the tadpole itself is a very simple, beautiful expression in terms of this gamma function, where this epsilon is your displacement from the number of dimensions d, and it is defined on the next slide as it should be. So here it is, this dimension, this epsilon here is going to keep showing up again and again. There are other functions which I've already shown diagrammatically. This b0 function, which is a 2-point function, or this one loop 3-point function, and these involve, yeah.
The previous slide that is gamma, it will be a gamma of minus 1 plus epsilon by 2, right?
Here?
The last slide. Is it should that be a function of epsilon by 2?
Yeah, but that depends on your definition of epsilon. Yeah. See, here we have this 4 minus 2 epsilon. You're right, there are different conventions in different books, so yeah, thank you for that. So that was an example of a hypergeometric function in one variable which is named after Gauss. There are extensions of the work of Gauss, first by French mathematicians Appel and Campe de Ferrier, and those are hypergeometric functions with more than one variable. For instance, with 2 variables, and this also shows up in elementary particle physics. Why should they actually show up in elementary particle physics? It's not really clear, but it just turns out through explicit calculations that very often they are just so happens that it is possible to express them in terms of hypergeometric functions. And here is a hypergeometric function which is denoted by f4 in 2 variables x and y. Appel defined 4 such Appel functions, f1, f2, f3, f4, and I'll also show you what these are. And I'd just like you to note that the parameters are sitting in the epsilon is sitting in the parameters over here, whereas the variables are always x and y, which are the kinematic variables of the problem. such as ratios of masses, momenta, etc. And then it goes on like this. Then the 3-point function is expressed in terms of the Appel function f2. And then there are further generalizations of hypergeometric functions from 2 variables to 3 variables, and they are very generic hypergeometric functions, and they are named after Italian mathematician Lauricella, and these are the Lauricella functions, which there are various families of Lauricella functions, and this is what they are over here. And the variables, again, you see are various ratios of masses and ratios of momenta and masses and so on. So this is the playground for our study and for our realization in terms of Mathematica programs. Just a couple of definitions, because without these I'll really not be able to make much sense out of this talk. So even BSc students and children who study for the famed JEE, they all know that 1 plus x squared, etc. It adds up to, please tell me, you made a mistake sitting in this row over here. Yeah, 1 by 1 minus x, right? And this has and this is valid only if absolute value of x is less than 1. So that is a geometric series that shows up in JEE exams. So that the generalization of that done by Gauss was not just to have 1, but he had these parameters that he calls A, B, and C, which can be reals. They can also be complex, no problem. So the first term has A times B divided by C. Then the next term has A times A plus 1, B times B plus 1 divided by actually factorial 2, C times C plus 1. And then it goes on. Then the next term will be A times A plus 1 times A plus 2, B times B plus 1 times B plus 2 divided by C times C plus 1 times C plus 2. So to carry this around is a bit of a problem. So what we have now is a definition of this object that is known as the Pochhammer symbol, which actually expresses this particular combination of symbols that shows up. So the most general definition of 2f1 involves this Pochhammer symbol, which comes in this an, bn. So this is how it is defined. Okay. So this is the Gauss hypergeometric function, so beautifully described in books on mathematical physics. And this obviously has to satisfy a differential equation, otherwise it doesn't make any sense why we should study such a thing. And here is the differential equation that it satisfies. It's a second order differential equation like so, which involves all these parameters A, B, and C. And then we also have to search for the singular points of this differential equation. And in this case, by just inspection, you can figure out that they are 0, 1, and infinity. This is very crucial because, as my friend here told me, this geometric series converges only when x is less than 1. Supposing you want to evaluate it for x greater than 1, then you expand it in powers of 1 by x. Okay? So that, and use the same series in order to do that. That's a very simple example. That is why you're able to do it. And to be able to go from the region of convergence to a different region where the function is defined, you have to do what is known as an analytic continuation, which is very straightforward in the case of this Gauss function of the hypergeometric function. It can also be done for hypergeometric functions. So life becomes more difficult when you do this, and you have to solve the various regions of convergence of this. And imagine doing this for hypergeometric functions with more than one variable. There it will not be just from 0 to 1, but it will be some region in the xy plane, and it may converge only in a small, let us say, a square in the xy plane, and you want to go everywhere in the xy plane, and you have to be able to perform analytic continuations, not because we want to enjoy ourselves, but because these Feynman integrals may require you to evaluate that particular hypergeometric function in a region where the original series is not converging. So you're driven by the needs of having to perform these analytic continuations. So our entire research is about these hypergeometric functions that arise in the evaluation of Feynman integrals, and to be able to do all these analytic continuations. But there are also other problems, because some of these functions become multi-valued, and so you have to be able to pick the correct analytic continuation on the correct Riemann sheet and all these things. So it's quite a challenge to do it. Yes, please.
So if we include more and more parameters in the hypergeometric function, that translates to the Feynman diagrams, like we include more interaction terms.
No, no, not like that. So the extension of the Gauss to F1 is called the PFQ, where you have P such Pockhammers in the numerator, and so this 2F1 and Q such in the denominator. So sometimes these Feynman integrals may evaluate to PFQs rather than a 2F1. So if you have more and more loops and more parameters, then the x, y will increase to x1, x2, x3, etc. And you'll have more and more variables. So we have to make a distinction between the parameters and the variables. Okay. So, but there are also all kinds of theorems which tell you what kind of functions you can expect at one loop, two loop, etc. Yeah. So as to complete these definitions, I just want to introduce for you this particular Appel function f2, which has these parameters. It has a larger number of parameters a, b1, b2, c1, c2, and two variables x, y. And just like in the previous case, you have powers of x to the m, y to the m divided by these various factorials. But the important thing to notice is that this summation index that we had earlier actually gets interwoven. So there is an interlacing of these summation indices. If you had everything m and n not talking to each other, that would be like a trivial multiplication of two hypergeometric functions of single variables. But this has obviously got more structure, and this m plus n shows up in this particular way. So this is what makes these hypergeometric functions non-trivial to deal with. Nevertheless, there are methods to deal with this. And this has a limited range of convergence. As I said, it's in a very small part of the xy plane where this original series converges. The F4 is a more complicated beast. It has this m plus n interlaced in an even more non-trivial way, and it is valid for an even more complicated region like this. This simple Lauricella function, for instance, has all this kind of index structure. So every such hypergeometric function is defined in terms of this defining series where you know how these indices are talking to one another. It's nothing very difficult. It's just something technical, and it arises in physical problems. So we have to deal with it whether we like it or not. Now, having introduced this, now let me introduce to you some examples that I have of integrals which are not Feynman integrals, but those that arise in other branches of physics. So let me begin here. We will have some examples of general interest which we have managed to solve because of developing methods to solve Feynman integrals. And I'd like to introduce to you something that is named after a very famous mathematician from this part of the world, but already been gone for over a century, Srinivasa Ramanujan. He has something known as Ramanujan's master theorem named after him, and it was G.H. Hardy who said that it really should be Ramanujan's because it's his personal property somehow. And then this Ramanujan introduced this for functions of a single variables, and more recently there have been extensions of that to functions of more than one variable which go under the name of method of brackets, which we have implemented, and then other integrals such as Mellin integrals, which also show up in many branches of mathematics, engineering, electrical engineering, etc. And we found various methods of solving these, and they are also intimately related to hypergeometric function theory and integrals. Okay. So as I already said, it's actually an extension of the Ramanujan master theorem, and this is what it says. Very simply says that you can evaluate a function that is known as f of x, which is expressed as a series in terms of the objects that enter over here, and it can be expressed in terms of a Mellin transform. So this is what Ramanujan had done, and this is what we have extended, and many others have extended, but we have applied it to a couple of interesting cases that go under the name of quadratic and quartic integrals, and these actually appear in the famous compilation by Grudstein and Rijik. And there are four such integrals that I want to draw your attention to. So here is one such, which is actually a single variable integration, which looks like this. So this is a quadratic integral like so. But you see on the right hand side, it has a very peculiar kind of result, which is expressed as a partial derivative with respect to all these things. And this kind of a partial derivative is then known only for integers, because you have the nth power sitting over here, and the answer is not known for values of n which are not integers. So we actually solve this problem by introducing this method of brackets, so that this particular integral we can express even for non-integral values of n. So those are two of the results, some of the results that we published using this particular method. Then there are more complicated integrals like this, which have these powers of n and m, and no such results are known in the literature, and we had the opportunity to publish them. And it turns out that by this extension of the Ramanujan's master theorem, these can actually be evaluated. And once again, you see that the answer for these turns out to be hypergeometric functions of this particular kind. Okay? So these are the results, but I want to show you, so this is still at the moment only of mathematical interest. Here is one more such example, but I want to introduce for you something else. For instance, integrals of this kind, which shows up in various branches of physics, where these are the Bessel functions and these are products of Bessel functions, and it's actually very difficult to evaluate some of these. So this method of brackets that we tried to use actually gives an answer which kind of fails, and you have to do all kinds of acrobatics in order to get the answer. However, there's a modified method which was proposed in the literature but not used for anything, which we used, and then we were able to actually evaluate using yet another package that we wrote, which is called conic hulls, and this answer left it for future generations to solve. And there are some classes of integrals that come under this rubric of Ising integrals that we were able to solve using this method of modified method of brackets, and here are some examples. So using this, we were able to actually find closed form expressions for these integrals with these various indices, etc., and these evaluate to something known as major G functions. So what I'm trying to convey here is that when you're trying to solve problems in one particular subfield, you're having to extend techniques, and it may help you to solve problems in other subfields of the subject. So just to finish this part of the talk, then I'll go to the Feynman integral, and even more significantly, I'll tell you about our Mathematica codes, because one of my objectives in being here is to actually do a commercial for our packages to encourage people to use our packages. Even though they arise in the context of Feynman integrals, they are of great generality. And I gave this talk in IISc a few months ago, and there was somebody who works in cosmology who said he also has similar integrals and he's going to try and use. So there you go. You have to take this back to Spain. Yeah.
So, but this, sorry, then you get something, you're saying you get close form, so you don't get, you're not solving numerical.
No. Our aim has generally been to be as analytical as possible to get answers in terms of known functions, such as other hypergeometric functions or Campe de Fourier functions or PFQs and so on. Nevertheless, while doing this work, we found that this F2 function, which is a very important, very popular function, the Mathematica implementation was giving wrong answers because it was going to the wrong sheet. And one of the co-authors of our package on F2 is Oleg Marichev, who has been working for Mathematica Corporation for 25 years. He is the author of a 5-volume set on functions originally from Ukraine, now settled in the US. So he also discussed and is one of the authors of our paper on this package. But now Mathematica has a new implementation of its function in the latest version also. Yeah. But one of the messages is that whenever you use these predefined functions in Mathematica or Maple or whatever, you have to always make sure that, that for known cases, you have to test them and make sure that you're getting the numerical value correctly. Yeah. See, I can type in an expression into Mathematica, but then if there are, fractional powers of something that is turning negative, you don't know what is the prescription that Mathematica is using in order to evaluate it. It'll give you an answer for sure, but you don't know whether it's on the right sheet or not. Yeah. Yes, with anything. So one has to be very careful with these things.
So,
Yeah.
does the expression remain closed form even if you include higher powers of x and f2? Like you're restricting it to x squared, right?
We have done some cases, but I'm not sure it is exhaustive. There are many, many open questions over here that you'll have to study and figure out for yourself whether it is solvable or not using those techniques.
So divergence series you will not get always the closed form expression.
So that is why we were using this modified method, which avoids that divergent series. Oh, you're talking about the Feynman integrals? There you have an expansion in powers of epsilon. And we have yet another other packages, which Shavik Bera, one of our former students, has written a very brilliant package where he is able to do a series expansion in powers of epsilon. So there are many tools available, and they are constantly being improved and updated and so on.
And then
Yeah.
typically, if you are looking at flow equations and things like that, at whatever you order, what you look at is for poles in epsilon, and then you move it to.
Yes, yes.
So does anything change when you look at these closed form expressions? Because all you're interested in that case is what are the poles?
Yeah.
To that order.
Yes,
to group
yes.
order, and then you subtract it out.
Yeah, yeah.
You get the z's, right? And from that you get the.
Yes.
Does anything change if you use?
See, it depends on what kind of diagram you're looking at.
Right.
It's only in very small handful of diagrams that expressions actually exist in closed form. So, so it depends on, even in the standard model, if you have massive fermions and so on, the number of analytical results you have is very few. So eventually these things, the coefficient of those things have to be evaluated numerically. And we know people do it. They use supercomputers and all for these things. Now this could also give you a check. You get an answer numerically and you have an analytic expression. There's a way of checking these things also.
So there's a systematic way of doing series expansions with your Fs.
Absolutely, absolutely. So those are also packages. It's now impossible to do any of these things manually after 1 to 2 loop orders. You cannot do. So the aim of all this work is to be able to, do these things for the order at which today's research requirements have imposed on the community.
So there's this very famous calculation of this G-2.
Yes, yes, yeah.
So your thing can do this?
That is at 5 loops in QED.
Yes.
So there, many of these master integrals are evaluated numerically. You can't, you're talking about 5 loops, which is extraordinarily complex. Yeah, so the last time it was done at 5 loops, I don't know how many hundreds of hours of supercomputer CPU time it has consumed, but these are all like phenomenal feats. Yeah. And there are softwares and hardwares built specifically for this purpose. The Japanese, of course, are the great experts in these things. Kinoshita had pioneered, spent 60 years of his life doing these calculations. Yeah, is it okay? Yeah. Yeah.
Unless you can't substitute x equal to 0 or 1, right? You do it close to that.
Yeah, yeah, close to that. Yeah, yeah. So this is so one of the other things is we have to repeatedly use various properties of hypergeometric functions. And here is one such example. I would like you to observe this particular thing. So here is this 2f1 for which I had introduced a series representation. But it also has, named after Euler, an integral representation, and it looks like this. So here is x the variable, and that x is sitting here in this 1 minus t times x. And these parameters a, b, and c are sitting as exponents of this t over here, of this 1 minus t over here, and this over here. Of course, this thing is symmetric in a and b, so it has some nice properties. So this is a very simple, beautiful expression for the Gauss hypergeometric function, and it's an integral representation. So the key thing is we are dealing with Feynman integrals. So wouldn't it be nice if some Feynman integral turned out to be an object that looks like this, and then you can therefore find an answer in terms of hypergeometric functions. Except that this is a very simple case. You could in principle have integral representations with more than one variable, x, y, if it's Lauricella, z1, z2, z3, and complicated objects like that, with the different parameters that showed up in the f2 and f4 sitting as various exponents of this, except that this thing is a function of only one variable, so it sort of satisfies an ordinary differential equation. If it was a function of two variables, it would be satisfying partial differential equations with a plural. So they are more complicated, and as we know, PDEs are very difficult to solve except in the most idealized situation, and that is why for hundreds of years human beings are still grappling with partial differential equations. So if you end up with integral representations like this, it would be very nice to turn them into hypergeometric functions by using a suitable theory. And that suitable theory was proposed about 30 years ago by 3 Russian mathematicians. This is Gelfand, Kapranov, and Zelensky, not the present president of Ukraine, but somebody with a very similar sounding name, GKZ. So this relation between Feynman integrals and Feynman integral representation and hypergeometric functions has only been discussed recently in the last 4 or 5 years. But again, there was no language or a platform on which you could solve these things. So along with my former students, the only good student is a former student, okay? Remember that, okay? So along with my former student, a bunch of very brilliant guys, all of them, without an exception, we actually wrote a wonderful package, in my opinion, wonderful package, which is called, give me a name, Feynman integrals GKZ. Feyn GKZ. That's the name that we invented, and the community actually has started to use our package, or at least they are citing it, where we gave a Mathematica realization for solving the integral representations that arise from Feynman integrals, not at arbitrary loop order of the type that Rajesh is interested in, but simplified examples for the moment under certain restricted conditions. We can solve these things, and we use a whole lot of other technology of Feynman integrals in order to solve these PDEs of the GKZ type. But before that, we also had to deal with various analytic continuations, and there's a whole science behind doing analytic continuations, and typically they're all named after various Germans and Swiss and so on. So Euler-Pfaff transformations, which are known for the 2F1s, or the Gauss hypergeometric function itself. So many different analytic continuations we have used in order to be able to provide for you a useful package to start from the original region of convergence of the F2, which is this rather small diamond over here. And by using all these different methods like Pfaff, Euler, etc., we can now tell you how to go to a region where, for instance, this red point is the point that you're interested in, and so on. So there are many, many different methods that we can use, and we actually managed to cover the entire xy plane, except for obviously where these PDEs are singular. Just like for the 2F1, we had singular points. For functions of 2 variables, what will you have? You'll have singular curves. And if you have functions of 3 variables, you'll have singular surfaces. So obviously on singular curves and singular surfaces, you will not be able to do it. But apart from those, we have been able to give analytic continuations of the F2, which can be evaluated everywhere. And this F2 is very important because through various connection formulas, you also know F1 and F3. F4 is very difficult, but this is, in a sense, it's a really comprehensive way of doing these things. So some of the packages that we developed are listed over here. As I said, Feyn GKZ. Then we also developed something known as MB for Mellin-Barnes, conic hulls, over here, published with these authors. We have a French collaborateur, Monsieur Samuel Friot, with whom we have done a lot of work. He has also worked with my former students. And then we have used other methods that is known as, for instance, Olsen, which is papers by an author from 60 years ago, who showed how to do analytic continuations of hypergeometric functions for more than one variable using the technology of one variable. So that it is called Olsen.wl. And then there's these Appel functions have been developed by all of us, including Oleg Marichev. So these are the various packages that we have to offer. But our work actually in this whole business of writing codes and trying to analyze Feynman integrals first appeared in this particular paper by myself, Abhishek Pal, and somebody, who could this person be? So you can also claim part of the glory for this. So we are very thankful for Sunetra for having participated in this project. Ratan Sarkar, who is now a postdoc across in IISc. So these are funny diagrams that show up in certain low energy physics applications where you may have particles of many different masses roaming around in these internal lines. And so you would like to analyze these diagrams in various limits, where one of the masses is very heavy, the other one is very light, both are very heavy, both are very light, etc. So that method is called the method of regions, which allows you to isolate and study diagrams of this sort. And we are very happy that this package also, which is the first one, is now quite popular. This also means that institutions in India can and should learn to collaborate with one another and produce products of value to the community. We now live in an era of deliverables and indices and markers and metrics and so on. So each one of these, we can use to improve our ratings. Besides getting onto SAP, SAP, are you all on SAP? This horrible, system on which you have to upload bills and grades and so on. Yeah. That's one way of going up in the rankings. The other way is to hire Nobel laureates, and the third way is to collaborate with each other. So I would recommend the last. So I have to do a little bit of this comedy. Otherwise, people think it's such a boring subject. What's the point, working on fields like this? So here is a big picture. So what we have done is we have analyzed Feynman integrals, and then we analyze them through this GKZ system using method of brackets, find solutions in generalized hypergeometric functions. Then we use this method of Olson, find analytic continuations, and if possible, try to evaluate them numerically or to give epsilon expansions. So here is a workflow for some of these things where you have to find the correct PDEs to solve and then solve them using techniques that mathematicians have invented for us that go under the names of, we teach this in MSc courses. Whenever you have an ordinary differential equation, we all say as if it's like a mantra. Now we use the method of Frobenius, and then we introduce a series solution, we solve it, which is true for ODEs. There is an analog of that for PDEs, which is called generalized Frobenius method, which is the correct way of solving this in this case. There's also another geometric solution. We have basically implemented all these ways of doing this using and combining a variety of softwares and backbones available in the literature, such as Topcom, which is based on Python. Now, I don't know anything about these things. Luckily, my former students know about these things. Let me give you a simple example so that I can give a little bit of life to all that I'm saying. Here is the same bubble diagram again with a momentum P1, two masses, M1 and M2, and here is a simple diagram like this. And let us ask, what does this evaluate to? So you can actually type in that particular diagram according to the syntax that we described, give the various ways of defining that particular diagram, and tell the computer to run it and to evaluate it. So the computer finds this bunch of exponents that I had mentioned earlier when I talked about the 2f1. So these are the various exponents, and then it solves it, and then it gives you the answer in terms of various hypergeometric functions, which in this case are not just the Appel function, but other functions named after Jacob Horn, another 19th century mathematician who had studied all these functions. So this is the reason why our packages become a bit popular, is we are able to link many different things and allow the user to find answers in a form where you have a closed form expression for these things whenever possible. Okay. Besides, as I said, it's not enough just to have a series solution. You always need to know where the series converges. Okay. So part of our package also involves a module that is known as ROC, which stands for region of convergence, and 2 because it's for functions of two variables, ROC. So this translates some of the theorems that were found by Jacob Horn, and it's all implemented in Mathematica. And then we can put it into this program and find suitable analytic continuations. We know where they're going to converge, and therefore it becomes useful. If I just give you a series and don't tell you where it converges, then it's of no use. So this is a whole science and subject to figure out where these things are. So here is a realization of how to evaluate this Appel 2 for various values of the parameters, and where this function is expected to converge. It adds a number of terms and then it gives you an answer. So I would like to encourage those of you who run into appel functions to use our packages so that you have a reliable evaluation of these functions. So this is the summary. We have found 44 analytic continuations, and then the package selects what is the most efficient, fastest converging analytic continuation in a particular region, and it also gives you a prescription for finding the correct analytic continuation because it's a multi-valued function because of the fractional powers of negative numbers. So everything is described in our paper and you can have a look. Here is one more topic. The original parent Feynman integral actually sometimes may be very complicated when you start out with something like this, and you'd like to reduce it to other Feynman diagrams which may be simpler in appearance and simpler to evaluate. So once again we go back to our favorite bubble diagram like so with these, exactly what we had earlier. And now we do again JEE problem with this, where you take a bunch of propagators like this and you write them out as partial fractions so that you produce more than one Feynman integral but with simplified propagators. Okay? So here is an example where the original diagram that you started out with becomes a sum of two diagrams with two massless propagators like so. So what this means is that the object, in this case it happens to be known analytically. This I2 had already promised you that it involves the appel function f4, which looks like this, these various variables. And on the right hand side you have Feynman diagrams where one of the particles is massless. So then it is easier to evaluate the right hand side compared to what it is on the left hand side, and therefore you find non-trivial relations between Feynman integrals. Let me see. Yeah. X1 and X2 are unknown linear combinations for which you can solve using the package, and then it gives you the answer for what X1 and X2 are. Okay. So it's an algebraic system which is solved by the package in order for you to get these. Thank you. So on the left hand side, if you have an appel function, on the right hand side also you have something which you can evaluate, and it turns out that we can actually get very simple results like this. This particular appel function with these parameters turns out to be something very simple that you may just find, you may be able to evaluate by hand. So these are what are known as connection formulas, where a complicated appel function can evaluate to simple known functions such as hyperbolic functions or just simple algebraic objects like this. So these packages and these studies also lead us into the study of finding new relations between hypergeometric functions. So what is to say that you have to stop with just the simplest JEE problem, this one, where you have only two propagators? How about more propagators? Well, you can do that too. Here you have D1, D2, D3, and you can recursively do this and keep working it out, and then you can prove some theorems about this particular process of evaluating Feynman diagrams of complicated arguments and produce them in terms of simpler objects like so. So let me again advertise for our package, done with my former student Shavik Bera, who is presently a postdoc in Korea, and Tanay Pathak is a postdoc in Kyoto. Tanay is a very curious character, like many PhD students. He was simultaneously doing a second PhD with other students. So he has as many publications in what he was doing with me as he has in this other field that is called complexity or Krylov complexity, things of the sort, which, needless to say, are far more highly cited than papers in particle physics. So he is now more or less working in that field, and he is so brilliant that within a year now, a neighboring institute has offered him a higher salary, and from 1st of April he will work in the same building but at a higher salary in a different institute. We should also learn to poach off each other. We are also boring and uninteresting people. So that's the way they do business in Japan. So this is our package. I'd like to encourage you all to download these packages. They are easy to install, easy to work with. Example notebooks are provided. and then you can work with this and also, you know, have fun, and I'm sure it'll help you in some of your research questions also. So here is this particular example. Since you asked me about x1 and x2, here is a solution for x1, you see. The answer is over here, just solved by the package.
This thing is related to Schwinger parameter.
Yes. Well, I wouldn't say so. It's not even that complicated. Yeah. But yes, it would be interesting to, you know, to combine these denominators and see how to do it in a different form also. See, that's the whole thing. Even this Feynman integral technology, there are a lot of methods. There's the Feynman representation, there's a Schwinger representation. More recently, there's something called the Lie-Pomeranski representation, which we found it to be useful for the Fein GKZ application. A priori, you don't know which one is useful for what. So it's almost like by trial and error, you try this, try that, and so on. It would be very good to systematize all these studies and to find what is the best way of doing these things. So let me finish. It's a little more than 50 minutes, so that we'll have some time for some questions. So what I have tried to do for you is to survey the problem of evaluation of integrals motivated by Feynman integrals. So I have tried to, you know, just mention, I have not proved any of these statements. One must generalize the Ramanujan's master theorem to the method of brackets. It turns out that this method of brackets in its original form often fails and has to be improved, what we call the modified method of brackets. So it has allowed for the evaluation of several integrals of mathematical physics, including quadratic, quartic, and also these Ising integrals. Feynman integrals are intimately related to hypergeometric functions. Tullio Regge actually wrote a paper about this in the 1950s, where he has given various examples of why they almost always have to evaluate a hypergeometric functions. Even in the GKZ paper, which is entirely mathematicians, they mention Feynman integrals. You know, for mathematicians to mention the name of any physicist is almost anathema, but they are Russian. Okay, they're Russian. Okay, so that's allowed. Yes. If they were French, no, c'est pas possible. So, Mathematica codes we have developed and published, and this allows for the efficient evaluation of multivariate functions. We have also studied analytic continuations and simplifications. Then Shovik has also written epsilon expansions, which is very important. And in our opinion, a lot of this work is just scratching at the surface, and a lot of this needs to be studied by younger people, and all this has to be developed and can be diversified also. Does it mean that everything is over? Well, far from it. I would say that we still need lots and lots of work in this particular field. Stefan Weinzierl has just published a book, just in the sense of 2024, which is about 900 pages. It's also available in the archive, but if you print it, your printer may, you know, burn out. But you can buy the Springer version of this book, all 900 pages, where he surveys so many different aspects. And the name of the book is Feynman Integrals. No way you can be wrong, or there's nothing uncertain. But integrals. Yeah, that's the name of the book. Yeah. But he shows many connections to many, many different branches of mathematics. See, many of these things, when you analyze them, there are also mathematical structures lying inside them. So a lot of which physicists don't really know. So, of course, Weinzierl knows, but others may not know. But each of these is a project in itself to learn what it is and to take it forward. But often he concludes that the best way of doing things is to go to the computer and evaluate it numerically. So there is a lot of work for those of you who are mathematically oriented to study these things and to work on this whenever the IPL matches are not on, for instance. There are other things like dispersion relations. One can write down dispersion relations for Feynman integrals. Even in this case, not much work has been done. People can do it. Then there are mathematical properties of these Feynman integrals that go under the name of Hodge structures, not sufficiently explored, in my opinion. There's a relation to algebraic geometry, number theory, combinatorics, etc. And we hear terms like iterated chain integrals, which are evaluated numerically. The entire theory of differential equations geared for these needs. There are Mathematica codes also, and across in IISc there are many experts who are working on these fields. Ravindran and his people have been working on such topics. Then there's something called theory of chords. So there are many directions of this kind that young people can easily explore and make significant contributions to. So there's a great advantage to having a name starting with A. So apart from Gohar Abbas et al., I am almost always the first author. So here we are. So the et al., I don't know who, et al. Stands for former students actually. So these are the various publications. The conic hulls was published in Physical Review Letters, and as expected, when it was submitted to Physical Review Letters, they of course want you to justify. There are the 3 I's: impact, innovation, and interest. So we said it's of great interest to us. So that didn't obviously convince the referee or the editor. So, but the referee said, look, I understand all this, but I need to see your code. You have to give me a code. So then, of course, we had to revise the manuscript and make the code legible. And a couple of months later, we got back a response. And we also suspect who it is. It's probably Smirnov in Moscow. He said, I have tested this. I ran it for several examples, and I'm convinced that it's correct, and therefore it should be published. So we are obviously quite pleased with this Physical Review Letters. And I also want to highlight that some of these, of course, are published in Physical Review. But this is the new thing. Many of these are published in Computer Physics Communication, which is like the flagship journal for many of these codes. Okay? Because there's also a technical editor in addition to the physics editor who will actually test this and make sure. So this is probably among the first contributions from India in particle physics to publish in Computer Physics Communications, and quite a bunch of them. And Shoaik and Tanay have also published, where I'm not one of the authors because they really did a lot of this work on their own, and doesn't seem to like the last page. Yeah, the second and the last page somehow it doesn't like. So this is basically what I wanted to talk to you about the excitement in this particular field, which required us to combine methods of physics, mathematics, as well as computer algebra. And I think that this is going to be the way the future is going to be, that nobody can really do anything very significant without the use of computers. And we consider this as one example where we've had some success in advancing this particular message. So let me stop here and see if there are any questions, discussions. Thank you. You can use that mic because I don't have it.
Yeah, fine. Then. So we would like to thank Professor Subramanian for giving such an.
That's my father, but that's okay. Yeah. No, that's my dad, but that's okay.
So now this is the time for Q&A session. Is there any question?
I thought Madras is the only place in the world where I don't have to explain first name and last name business, but evidently, no, it's not the case.
But
Yeah.
unlike you, I mean, it's opposite for me, right?
That's your own fault.
Yeah. Okay. No. The thing
Yes.
is it guaranteed that every Feynman integral will give you GKZ, hypergeometric?
It's not at all obvious.
There's
It's
no
n-
theorem.
These are all, I think, early explorations. Okay, and the examples that we have studied are some of the early examples. So, and these correspond to what are called non-resonant cases. There are other resonant cases, which Albrecht Clem, of course, pointed out to us. So, yeah. Yes.
Fascinating talk.
Thank you.
Wonderful. Just a quick question. You made a mapping between Feynman integrals and some hypergeometric functions that
Yes.
correspond function in particular.
Yeah.
I'm wondering to invert this, stand it on its head.
Yes.
You look at the 24 symmetries of the hypergeometric function,
Yes.
the Kummer relations.
Yes.
What implication would it have in your models for the diagrams themselves?
Yes.
Of the process?
Yeah, this is an excellent question. I'm aware of this particular paper, but so far we have not applied it to any of these things. It's a project for the future, definitely. Yeah.
The other question was that when you have hypergeometric functions in two variables, as you pointed out, the singularities become line singularities, so to speak,
Yeah.
and moving singularities. Is there any occasion in which you come across a natural boundary, so you can't continue?
This is again a very good question. It turned out for the case of F2, we were able to cover all the regions. For the F4 also, there are some cases where there are small regions which we call white zones. That's what Samuel started calling them. But it's never obvious that you have exhausted all possibilities. You may have tried Pfaff Euler and you couldn't cover a certain region, but it is not exhaustive. So there may always be some transformation that you didn't know about, which you couldn't do over there. So it's sort of like a search strategy, and you have to keep doing it until you find it. So that is, I think, as far as two variables are concerned, one can more or less clean up the whole thing. But beyond that, it's almost impossible. For these Lauricella functions and sunsets and all, there are only small isolated islands where you actually have series which converge. There are large regions which cannot be covered.
Final question. In your experience, is there any occasion in which dimensional regularization doesn't work?
Dimensional regularization is very tricky when there is gamma 5 shows up. So in the cases of calculations with anomalies, there are problems for implementing simultaneously dimensional regularization and gamma 5. So again, there are various prescriptions going under the names of Veltman and Passarino. There are many different prescriptions to do these things, which actually becomes a more acute problem for lattice gauge theory on how to do some of these things. It's not in my experience because I don't really work in that domain, but other colleagues do run into these things, and there are difficulties always with anomalies and so on. How they solve it, it's a technical exercise on how they solve these things.
So in cosmology, we have similar integrals.
Yes.
So they are different in a sense because what we do is integral of Henkel function and
Yes.
Bessel function, multiple integral of
Yes.
this kind of thing, and always we get into trouble.
Yes.
And often like high oscillating
Yes.
functions. So these packages can be somehow used or modified in a way that
I absolutely hope so. We need many people to participate in this activity of taking this up and seeing under what circumstances it may fail or it has to be extended. The theory is also explained, for instance. So you may have to suitably modify your theory for your particular Hankel function and see what happens. The very peculiar thing is that many of these integrals, they get related to various questions of algebraic geometry, which mathematicians have studied for no particularly good reason, I suppose. Don't tell anybody. But they get related to other properties of these mathematical systems. So in principle, yes, every one of them, one must be able to find an answer. Whether in practice we are able to do it or not, one doesn't know. So yes, we all have to do this. Raghu sent me a paper with some cosmic integrals. Raghu is not here. Oh, you're here. So he also had some integrals, and then one of the things we plan to discuss is those things. I've forgotten who the authors were of that paper. Harkani Hamed and company, was it? Yeah. Yes. Yes. It's all work in progress, so to speak.
Since it's a colloquium, I have a very
Yes,
general
of course.
question.
Yes.
Famous Wigner statement that
Yes.
unusual effectiveness of mathematics in describing natural phenomena
Yes.
comes out very clearly in your talk.
Thank you. Yeah.
So much mathematics, even in a perturbative method.
Yes.
Imagine going to Feynman path integrals.
Yes. Yeah.
To explore.
Yeah.
Are there attempts to understand non-perturbative phenomena by considering, for example, carpet regulation using such things?
The only direct answer to that question is again the lattice approach to solving QCD. It's the only truly non-perturbative solution we have to the strong interactions. For other phenomena, I see for something like QED, perturbation theory is so effective that we don't know what it even means to solve some non-perturbative version of QED, whereas for the strong interactions, we have no option but to do it. Of course, you have string theory and so on, and string field theory, and that is of course another project for the future, really, for the 23rd century, probably, when many of these questions will get answered. The thing is, this statement of Wigner, my own personal reaction to that is mixed. Why should we think of mathematics as being somehow alien to physics? It's also part of nature, part of work that physicists, mathematicians, chemists, everybody does. It's partly because the traditions and the languages are so different, and these communities live in their own silos and don't talk to each other. Now, we really need these communities to talk to each other. Even at the lunch table, you find mathematicians sitting separately from the physicists. But if they sat together, maybe they will start to solve problems together. You know, exchange of ideas. Okay, so you're calculating some curve or the other, and Suresh here is calculating, I don't know, algebraic curves with his Mobius, Matthew functions. If these guys talk to each other, I'm sure they could solve things. It requires effort from all communities to do these things. See, now I'm a senior citizen, I can say whatever I like.
Anand, that would be a conversation between two physicists
Yes.
who are also mathematicians.
Yes.
So that doesn't...
Yes. So anyway, I really feel that we should also demystify mathematics and make it more accessible. If the language is so arcane and so difficult that the idea it may be possible for them to convey to us, and we could discuss with them and give problems for mathematicians to solve. Sure, we should do it, I think.
So I think before the world goes completely numerical,
yes.
it should happen.
I thought you were going to say nuclear, but you only said numerical. Okay, so.
There is also artificial intelligence.
No, even numerical methods, what confidence do we have that it's converging to the right answer or not? As somebody mentioned, highly oscillatory integrals and so on. We don't know whether the answer that you're getting at some order is correct or not, unless you know whether it's an asymptotic series and you have bounds on errors and so on. How do we know that the answer is right? Just because a computer is giving a number doesn't mean it's correct. So, of course, we don't have problems like people who do weather predictions. Even if I make a mistake, it's not going to lead to a flood somewhere. But for other subjects like weather predictions and economics and so on, we need very reliable methods. Anyway, it's a short answer made long.
Those will involve PDEs
Yes, exactly. Yes.
and nonlinear PDEs.
Yes, absolutely.
Is there any questions? So if not, let's
You have to ask a question.
let's-
No, just
let's
joking.
thank the speaker today.
Thank you very much. Thank you.
Something
Thank
from
you very
the
much.
department. I think you'll enjoy it.
Yeah, it's a